welcome everyone to the final day of the QIP here. So if you have survived so far, I'm sure you'll survive another session. So we have three amazing talks today on quantum PCP theorem, unique games conjecture, and non-commutative CSPs. Our first speaker is Itai Arad from Center for Quantum Technology, Singapore, and he's going to talk about quasi-quantum states and quasi-quantum PCP theorem.
Okay, thank you. So this is a joint work with Miklos Santha from the Center for Quantum Technologies in Singapore. Okay, so let's start. So I'm going to talk today about the distance between classical constraint satisfaction problems, CSPs, and quantum Hamiltonians. And as we're well aware of, there is this river of tears separating these two things. And the reason is that the structure of classical CSPs is much simpler than local Hamiltonians. And therefore, we have so many more results. But still, we're able to prove things about quantum Hamiltonian complexity, mainly because we have this nice map that maps basic concepts from CSPs to local Hamiltonians. So assignments go to quantum states, local constraints go to local Hamiltonian terms, number of violations go to energy, etc. And this map has managed to take us quite far, and using it, we can prove many things that are many similar results in the quantum regime that are taken from the classical regime. So for example, the Cook-Levin theorem saying that 3-sat is NP complete. Kitaev showed that 5 local Hamiltonian is QMA complete, and max 2-sat is NP complete. We can use reductions to strengthen these results. So max 2-sat is NP complete, and on the other hand, 2 local Hamiltonian is QMA complete. 2-sat is in P. The same thing goes for 2 local frustration-free Hamiltonian. This is also in P. So there are many similarities between these two worlds. But nevertheless, and this is the subject of this talk, there are still many, I think, important differences between these two worlds. And to begin, first of all, Kitaev's proofs of the QMA hardness is substantially different from Cook-Levin. In Kitaev's proof, we're using the history state, and we're using just one register of qubits in which all the history of the computation is encoded, whereas in Kitaev's proof, there is every time slot has a new set of bits on which we encode. So this is substantially different. And for example, local Hamiltonian is a promise problem, whereas SAT is a decision problem. And another important difference is that in quantum, classical 1D, constraint satisfaction problem on a line, they can be solved efficiently using dynamical programming. But in the quantum world, we see that this is QMA hard. Okay, there is a famous result from 2007. And another one is that CSPs have search to decision reduction. We don't have that, or don't seem to have that in the quantum world. Okay, and finally, I think this is, which is the main motivation for this talk. We have a PCP theorem in the classical world, but we only have a conjecture in the quantum world. Okay? Now, I want to claim that a major reason for all of these differences is the fact that quantum states generally lack a simple tensor product structure, whereas the basic ingredient in classical CSPs, which is the assignment, has a very simple tensor product structure. I think this is the main ingredient for these differences. And to be specific, when we look at a classical assignment, like this one, for example, then, so it has this simple tensor product. Because of that, local marginals very easily determine the global assignment, okay? If we know the, if we know what happens at every bit, we know easily what is the assignment of what is the global assignment. And finally, because it has this simple tensor product, then information can be easily copied. And there is a sense to what we mean by copying local bits. On the other hand, in the quantum world, we have entanglement. So we have a superposition of assignments, if you will. And therefore, instead of a simple tensorial structure, we have entanglement or correlations. Local marginals no longer determine the overall quantum state. In fact, it is even QMA hard to decide if they are consistent with some global state. And of course, there isn't much sense in copying local information in quantum. Okay, I mean, at least it's not as easy as in the classical setting. So, and to give you an example where this thing comes about, for example, in trying to prove the PCP, so look at a simple step in Dinur's PCP proof. This is called degree reduction, where we have one vertex with a lot of edges coming into it. Every edge is some sort, encodes some sort of a constraint, and we want to replace it with a cloud of variables, which all should be the same, and there should be some equality constraints between them. Okay, so classically, it's almost trivial to do it, right? We just define this new constraint graph, and then if we are in the yes case and there is a solution and we want to see what happens in the new graph, then we can just copy locally the information of this solution. However, quantumly, what can we do? It's not clear what type of constraints we should put here. It's not clear how to copy this information. Okay. So coming back to this gap between classical CSPs and quantum Hamiltonians, what I want to suggest in this talk is that we can somehow bridge these two worlds. And I want to suggest that there is an increasing set of frameworks with some locality constraints K, such that when this locality constraint is 0, we get the classical framework of assignments and CSPs. And when it is equal to n, the number of bits or qubits, we recover the quantum setup. And I want specifically to say that we can analyze the constant K case. And furthermore, this is what I will call quasi-quantum states. And I will show you that this case, first of all, is still classical. So everything here is still NP. But it is substantially different than the CSP case, and it is much closer to the quantum case in the sense that the basic ingredients, the basic object on which we try to optimize is no longer a simple assignment, but instead a distribution, a classical distribution of assignments. So it also, like the quantum case, lacks a simple tensorial structure. And therefore, many of the difficulties that we encounter in the quantum case, we shall also be able to see them and analyze them in this case, but now it is simpler because it is classical. So it might teach us something about how to deal with the actual quantum case. Okay? So what is the idea? So the idea is, as I was saying, is to study a classical CSP, but instead of over assignments, over distributions of assignments. So imagine this is the set of all possible distribution. It's a polytope of the distribution over the assignments, and we want to concentrate on the subset of this set. And in this subset, we will consider a local Hamiltonian, and we will consider distribution of assignments. And once we are given a distribution of assignments, we can define the average energy, and we can minimize over all possible distribution to obtain the ground energy in that model. But I would like to stress that it is extremely important that we're dealing with a subset of all distribution and not taking all of distribution, because otherwise, if we would have taken all distribution, the ground state, which is an extreme point of this convex set, would have been on the edge of this polytope, which is, again, a pure, a sharp distribution of a particular assignment. So we would be back in the simple tensor product state. So it is crucial that instead of looking at all distribution, we look at a convex subset of this distribution. And the question is, OK, so how do we define this subset? So to define this subset, we're actually going back to the language of quantum operators. And what we will do, we will relax the positivity constraint of a quantum state. And how we do it? We will use a fixed basis of a POVM, of an information incomplete POVM measurement. So we are fixing 4 POVM elements, E0, E1, E2, and E3. You can make it symmetrically information incomplete. So for example, we can take 4 pure states on the Bloch sphere and construct these, which are on a tetrahedra, and construct this POVM like that. And then we can extend this single qubit POVM to the entire system by taking tensor products. And then every element of this POVM will be defined by E alpha, where alpha is this tuple of alpha 1. It's this assignment, essentially, of alpha 1 to alpha n. Now, once we have fixed this, we can define what a quasi-quantum state is. A quasi-quantum state is an operator. So it is a Hermitian operator. It has trace 1. It is a multi-qubit operator. But instead of asking it to be positive, we're asking for a weaker condition. The first condition is that if we measure it with this particular basis, we should get something which is positive, non-negative. And the other thing is that if we look at it locally, so we trace out everything and we just look at the marginal or the RDM, then it should behave like a quantum state. So it should be completely positive. So these are the 2 conditions that we are using, local positivity and global positivity. And you can convince yourself that the first 2 conditions actually define a probability distribution. If we measure our operator using this POVM basis, we get a set of numbers which are actually, because of the first 2 conditions, give us a probability distribution. So there is and because it is information incomplete, then there is a one-to-one connection between probability distribution and this type of operator. So I will exchangeably talk about these 2 concepts. Okay. So in some way, what we are talking about, because we relax the positivity constraints, then now we're talking about a superset of all quantum operators, of all quantum states. And so the picture that we should look at is the set of quantum states around which we have the set of quasi-quantum states, k-local quasi-quantum states, and the outermost set is the set of all possible distributions. And as we increase the locality, we are shrinking the quasi-quantum states, and we are collapsing to the quantum state. Okay? Now, there's an alternative way, equivalent way of talking about quantum states, which uses the dual basis to the POVM. So the dual basis is a set of 4 matrices that are orthogonal, co-orthogonal to the POVM. Of course, because if the POVM is completely positive, then these guys cannot be positive operators. So actually, each one of them has 1 negative eigenvalue and 1 positive eigenvalue, but together they are co-orthogonal to the POVM. And so we can extend this also to the full space. And then it is very easy to see that if mu alpha is the probability distribution that we get from a specific quasi-quantum state, then this quasi-quantum set can be written as a convex combination of these d alpha. Okay? So that leads us to define an equivalent way of what is a quasi-quantum state. So a quasi-quantum state is anything that we can write down with a probability distribution over these d alpha that also satisfies the local positivity condition. Okay? And this is the thing that gives us the fact that we're not the full polytoph of probabilities, but a smaller convex subset. Okay? So from now on, I will talk about quasi-quantum state mostly in this notation. Okay, so once we have defined the quasi-quantum states, we can now ask what is the complexity of minimizing the Hamiltonian on this set of operators. So we are looking now at a regular quantum Hamiltonian with m entries, and we can now define the quasi-quantum ground energy as the minima of all possible energies of all states of all quasi-quantum states. And we can define just like in the quantum case, we can define the local Hamiltonian problem as a decision problem. We are given the promise problem. We are given a local Hamiltonian. We are promised that the quantum energy is either below A, this is the yes case, or above B, and we have to decide which is which. And the question that we want to ask is, okay, how complex, how difficult is this problem? And our main result is that this is an NP-complete problem over a huge range of promise gaps between A and B. So it is NP-complete starting from an exponentially small gap all the way to a gap which is the size of the system, which gives us a PCP for these two things. Okay? And that's why I'm saying that essentially this problem is a classical problem because of this NP completeness. Okay. So how much time do I have? 5 minutes, okay. So let me shed some details about the proof. First of all, we want to show that this problem is inside NP. So the way to show that it is inside NP, I mean, okay, we want to show that the ground state which is given by some probability distribution has an efficient polynomial description, right? On the surface, this looks a bit tough because it is described by some probability over n variables, which is an exponential object. But our idea is to use this construction by Itai from 92 that says that every multivariate probability distribution, for every one of them, there exists a sister distribution that, first of all, has the same local marginals as the original distribution, and on top of that has a polynomial support. If we take it and we plug it into the quasi-quantum state, then we automatically get that for every k-local quasi-quantum state, there is an efficient sister state that has the same marginals and therefore has the same energy, but on top of that has an efficient description. So that's what puts it inside NP. Okay? Now, and the way Itai proved that was using a Karl-Theodori theorem. He was mapping the probabilities into the space of marginals and then using Karl-Theodori theorem. So that's the way that proof works. Now, proving hardness is substantially more difficult, just like in Kitayev's proof, perhaps. Essentially, what we do is we construct a gap-preserving reduction from a PCP four-coloring problem to a three-local Hamiltonian. We start, in some sense, from the natural four-coloring Hamiltonian in the language of quasi-quantum states. So it will be this type of Hamiltonian. This term here will penalize you whenever, give you an energy penalty whenever two vertices are colored the same, okay? And in fact, it is, you can check it that it is actually up to a scaling and overall, and shifting, it is actually the antiferromagnetic Heisenberg model. If we check the average of this Hamiltonian with respect to some d alpha, we see that it is exactly the number of violations in alpha, and therefore, for a general quasi-quantum state, it will be the expected number of violation, and therefore, soundness is very easy. I mean, soundness is extremely easy in this case. What is not easy is to show that if you do have a coloring solution, then you also have a quasi-quantum state with a zero energy. This is extremely non-trivial. And the problem why it is not easy is that if we assume, for example, that this is a good coloring of the graph, then we might think, okay, so let's try this as a quasi-quantum state, and it will have a zero energy. But the problem with this thing is that this is no longer a locally positive operator. Remember that these Ds are extremely ugly beasts. Each one of them has one positive eigenvalue and one negative eigenvalue. So locally, this is very, very far from being positive. So instead of using a single guy like that, what we need to do is we need that in the yes case, we will have plenty of solutions that will somehow cancel the negativity of each other. So we need to have this type of construction, and that's what makes the proof much, much more involved and complicated. So I won't go over it, but I will give you some elements that we have in the proof. So the proof goes by, first of all, working with a certain set of graphs for which we can always decompose them into 3 subgraphs with non-overlapping, with different set of edges. And each one of these subgraphs is a simple graph. It's either a tree or a simple loop or a bipartite graph. And the idea is that each one of them has many, 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 many solutions. And then what we want to do, we want to take all these solutions and combine them together with this D, with this specific D, in order to cushion up the negativity. And in order to do that, what we also do, we use this, what we call a scapegoat qubit. So we add some more qubits here to the system, each qubit for each one of these subsets, and we condition this solution on these qubits. In some way, this enables us to control the energy violation and enable us to combine all these solutions together. And I would note that, first of all, the resultant Hamiltonian is now 3 local instead of 2 local. And also, it is highly frustrated also in the yes case. Okay? It's not 0 in the yes case. It's simply less frustrated than the no case. Okay, so to summarize, we introduced k-local quasi-quantum states as a classical constraint satisfaction problem model over distributions of assignments. These are relaxations of the proper quantum states, and therefore the ground energy that we get is a lower bound to the actual ground energy of the model. We proved the PCP theorem for these guys, and we showed in that sense that that the lack of a simple tensorial structure is not, is not an obstacle in that sense for proving PCP. And we can actually, in some sense, go over through the proof of Dinur and try to see what happens in this setup, how it behaves. And when it goes to open questions, then there are many open questions. So first of all, what does it tell us about the actual quantum PCP conjecture? I still don't know. I mean, this is an ongoing project. There are some nice, I think, insight that we can get. First of all, the resultant Hamiltonian is not 2 local, it's 3 local. So this kind of bypasses this no-go of Brandau and Arau, which was set for 2 local Hamiltonians. Second thing, I think, which is important, that it is highly frustrated. Okay, so I think this is also a direction we should look in the general case. We should look for cases where the yes case is also frustrated. And then other problem would be, for example, to see how far this model resembles the quantum case. So is it still hard in 1D? I mean, I don't think we can use dynamical programming to show that it is easy. So it would be nice to show if it is still hard here. What about search to decision? And of course, it would be interesting to see what the NLTS conjecture says here, just because we also have a quantum proof. So it will help us to bridge these 2 things in a better way. These quasi-quantum states can also be used as a numerical tool. We heard about all types of relaxations of QMA problems into SDPs. This is a much stronger, a much tighter bound in some sense, because we are, in addition to demanding local consistency between the RDMs, we are also demanding the existence of a global object. So that means that the energy that we will get from here will be a better lower bound than all these SDP and Elster relaxations. The flip side is that we are trying to solve an NP-hard problem. But it's a classical problem, it's not a quantum problem. So there might be some interesting numerical ideas to use it as a tool. And finally, it would be interesting if we can bound these the difference between the quasi-quantum energy and the actual energy. If we can find a bound, that might be actually used to disprove the PCP theorem, because that will give us some sort of a classical witness for lowering the energy of a quantum system. And finally, it would be interesting to find a natural computational model over these states. Thank you.
Right, yeah. We have time for a couple of questions.
I think I might have missed something, which is, why doesn't any hardness of the quasi-quantum optimization just follow naturally from NP hardness of classical optimization?
Well, because it doesn't follow naturally because of essentially because of this thing. You want to reduce this particular problem, but if you take a classical problem, your basic elements are assignments, but you cannot translate them automatically to quasi-quantum states because they are not quasi-quantum states, because they violate the local positivity. So all the hard work was about establishing this point. And also, you cannot just take, for example, classical problems and embed them in quantum problem as a tensor product state, because then the quasi-quantum energy might be actually lower than the classical energy. So both of these directions don't follow up easily. That's why it's not trivially follows from classical hardness. It does follow in the end, but after quite substantial work.
I see. Thanks.
Yeah, thanks for the nice talk. So I was just wondering if you could clarify your comment about Brando and Harrow. So there's two things I was wondering about there. Are you saying that when you have like a sort of quote-unquote high-degree 3-local Hamiltonian, then the Brando-Harrow kind of product state approximation is not an avenue towards kind of
what I'm saying is that the Brando-Harrow depends heavily on the fact that you have two-body interactions. And there is an example, I think, counterexample by Anurag and his student that shows that in a 4-local thing, it doesn't work.
Oh, I didn't know that. Can I also ask, I believe that in Brando-Harrow, there's also a rounding procedure, like a correlation rounding based on a sick PVM measurement. Am I?
Yeah.
So how does that, is that related in some way? Or is
well,
it just
that was part of the inspiration to go into this thing, yeah.
Okay, thanks.
Yeah, maybe one last question. Yeah.
Okay. Have you thought about whether there's an extension of this model that's plausibly MA hard? Because I guess this one is contained in NP.
No.
Okay.
Yeah, I guess perhaps like when you make the K large enough, like log n or something.
Yeah, it could be. Yeah, okay. It could very well be. Yeah, that's true. Yeah, because for finite guys, it is by definition in NP, because of this Pitofsky construction.
Okay. Thanks.
Okay. So let's thank Itai again.
Thank you.